Welcome to the first KC test talk of this semester. Okay, I'm the speaker for today. Okay, this is my name. Okay. And this is the title of the talk: Doing parallel computing on your laptop, desktop. Okay. The talk is supposed to be 15 minutes, but I'd like extra few minutes. So I try to control my talk so that I can finish before 12:50. Okay. You would need 30 minutes. I'm sorry, 30 hours to generate such an image. 30 years ago, okay? And 10 years ago, to generate an image like this one here, you only need 1 to 2 hours. 1 to 2 hours. Today, if you want to generate an image like this one here, you need less than 15 seconds. What's the difference or why? And the question has to be answered in 2 senses. First of all, how come an image like this one would take so much time to generate? Well, then you have to understand the nature or how ray tracing image is generated. Okay? You generate the ray for each pixel of your screen, right? And this process is a recursive process. You find the first intersection point, and then you determine if that point is in shadow, and then you compute the contribution for that point from neighboring objects, all right? And if the object is transparent, then you also have to compute contribution from light sources behind that object, okay? And remember that this is done for each pixel of your screen. So totally the time required for generating such an image is what? The time required for each ray times the number of pixels of your screen, right? So that's why you have to take a lot of time to do the generation. Okay? Now, how come that we get improvement so dramatically, okay, during the past 30 years? So second, why can we get improvement on execution time that much in 30 times? Okay? Some 200 folds in 30 years, 240 folds in 10 years. Well, that is because the improvement of hardware, okay, or simply GPU. Okay. So with the, with the help of GPU here, we have what? We have a pipeline to do graphics now, right, on GPU. Right? And every step in the graphic pipeline is done by a piece of hardware. That is why to improve our performance so much in 30 years and so much in the last 10 years. Okay? So you start, the entire process is triangles-based. Okay? Each object is approximated by a triangular mesh, and then for each triangle you have to go through this process here. Okay? Vertex processing, primitive processing, cross gradation, and then eventually compute intensity for each, or color for each pixel of the triangle, okay? And if necessary, do texture mapping, and then determine which pixel is visible, which pixel is not visible to the viewer, okay? So in order to do this, we need to generate a vertex schedule code program in a fragment shader program. Okay. This has to be generated separately. Okay. But your C program, your C++ program here, okay, does all the administrative and the logistic steps, okay, to ensure that these programs will get the parameters, get the buffers required, for communication between CPU and GPU, and then go through this entire pipeline process here, right? However, conceptually, okay, so this is what you have to do in order to do graphics on your laptop or desktop. Okay? You have to generate vertex shader code, fragment shader code, and have this code installed on GPU. Well, actually, this code has to be compiled separately, compiled, linked, and activated separately, and then loaded onto the GPU, so GPU can execute those instructions and get the results sent to the display monitor or to the screen. Okay? But this is only for what? This is only for so this is the vertex shader and the fragment shader will do. Okay? Get parameters, get buffers from the C++ program, have those things sent to the pipeline, processed, generate colors for each pixel of the triangle, and generate texture, coordinate, etc., and then determine visibility of each pixel. Okay? And then have the results sent to the display screen. All right. However, implementing ray tracing, even using OpenGL shaders, is challenging. I'll tell you why. Because the large number of computations required for ray tracing process can even tax modern GPUs. Okay? Recall that the time required for the ray tracing process for 1K by 1K screen is what? We need to do ray tracing for each pixel. And the number of pixels of your screens is what screens, 1 million. So the total time required is the time required for each ray times what? Times 1 million. So no matter how small you make this part, still you have to face this big number constant. Right? And this is the main obstacle to overcome. Besides, OpenGL is ray tracing is a recursive process, and OpenGL shaders do not support recursion. We have to implement a recursion ourselves, which means that we probably have to repeat the pipeline several times, sometimes more than hundreds, okay, if the depth of the recursion is big. Okay? So this means what? This means this pipeline here is not good for it's not good for ray tracing process. Not good. Well, then how will we be able to reduce the computation time from 30 hours to 1 to 2 hours and eventually to less than 15 seconds? Well, fortunately, we can do ray tracing in parallel using a compute shader. So what does this mean? Modern GPU may have 4 to 8 cores, but a modern GPU can have as many as thousands of cores. Okay? So this is a modern CPU. You have 8 cores, okay? Core 1, Core 2, up to Core 8. Here, cores 2 to 7 are in between. Core 1, Core 2, Core 8. But for modern GPU, you have more than, most of the time, more than 1,000 cores. Okay. For instance, for NVIDIA GeForce 10, you can have as many as 700 to 4,000 cores. For AMD Radeon 400, you can have as many as 1,000 cores to 2,500 cores. This example here is NVIDIA GeForce GTX 660 Ti. It has 1344 cores. Okay. So what does this mean? This means that we can develop a piece of code called a computer scheduler program, okay, for the task to be performed by the GPU, such as the ray tracing process. Okay. Each process is exactly the same, only that the data set may be different. Okay. So here we have to duplicate copies of the computer scheduler program, one for a core of the GPU. So if you have 1,000 cores in your GPU, then you can make 1,000 copies of your computer shader program. Okay. And then assign a data set to each copy of the computer shader program, and then set the assigned 8 cores to perform the assigned task on the assigned data set independently. This means that all those cores can perform the same task independently at the same time, only on different data sets, for instance, on different rates. Okay? So this is the concept now. Okay? You need to generate a computer shader program. Okay? This is not the job of your C++ program. This is your job. You have to generate such a computer shader program. Okay? Make copies of this program on as many cores as possible. Okay? So you generate a copy for each core that's available to you, and then you assign a data set to each copy of that computer shader program, okay? And then set them to perform separately or in parallel. Okay? So each core here would work on its own computer shader program, generate a result for the given data set, and then in this case for ray tracing program, you generate a result for each pixel. So you put your result into a texture, 2D texture image. Okay? So this is how ray tracing is done now, only that you wouldn't see a picture on the screen. Still, you need a vertex shader code, you need a fragment shader code to process this texture image. Okay? Meaning that this image has to be sent to this pipeline here to have this texture image showing on screen. Okay? But the most difficult job now is done by this part, okay? By the cores of your GPU independently or in parallel. So this is the concept. Okay? So you have to not load your, well, first of all, because you have to create your compute shader program, your vertex shader program, your fragment shader program, and have those programs compiled, because GPU doesn't understand C++. It only understands its own language. Okay? So this program have to be written in the language that GPU can understand, and then compiled, linked, and executed. Okay? For GPU, sent to GPU so GPU can execute those instructions. Okay? So it's like, you send your orders to some foreign manufacturers, okay, such as manufacturers. But those orders have to be written in Chinese so that they will understand what each order is for. And then once the order is processed, or once the product is produced, then you send those products back to what? To CPU, so that I'm sorry, to the vertex shader program and fragment shader program, so that the result or your image can be shown on screen, can be shown in your screen here. So the point here is that you have to write your own complete shader program. You have to write your own vertex shader program. You have to write your own fragment shader program in the language that the GPU can understand, or so-called GLSL language, right? Okay.
I have a naive question. There are not enough GPUs, so that if GPU serves the purpose of computing this, of taking care of one pixel. So we also have to assign pixels to GPUs.
Yeah, you have to assign rates to those cores.
Yes.
So if you only have, say, 2,000 cores, but if you have 1 million rays or pixels, of course, then you can only process 2,000 rays at a time. So in that case, means that you have to repeat the process 50 times, or I don't know, 1 million divided by 2,000, 50, or so in parallel, that means that you can use as many cores you can get from the GPU in parallel.
So who takes care of this assignment of rays?
Who?
Or what?
Your C++ program. Because there's a command, there's a command for the GL dispatch compute, okay, for your C++ program to what? To define how many cores. Like in this case, 4 in X direction, 3 in Y direction, and 2 in Z direction. So this means 24 cores will be used for this task here. If 24 cores is the number that you can get, of course, then you have to repeat this process several times. Okay? And then, of course, you also have commands to what? To assign data set to each core. Okay? Assign data set to each core, and then set the core to perform the task separately. So this is the part here. You create or you define cores that should be used for your task, meaning that you have to duplicate as many copies of your computer shader program, and one for each core, and then you assign each core a data set, and then set the core to work on that particular data set on a given task separately. So this is the concept. Usually this is done, we classify this as a two-phase process. First, you use cores of your GPU to carry out, for instance, the ray tracing process. In this case, you get a two-dimensional texture image. And then you render the result image, okay, through your vertex shader program, through your fragment shader program. Okay. So this is usually classified as a two-phase process. You have to generate a ray for each pixel here. right? This means that you have to make a copy of your computational program, assign that copy to a particular core of your GPU. And the ray tracing process, okay, the reason that the ray tracing process cannot go through the graphics pipeline of your GPU is because ray tracing is a recursive process. In what sense? You generate a ray for each pixel. S is a pixel of the screen. You generate for each pixel of the screen. You get the intersection point of this ray with the first object. Once you have the intersection point, this is your first step. Once you have the intersection point, then you have to determine if that point is in shot. That is, you have to check if a ray from this point to the light source would hit anything else before it hits the light source. So this is the second step, to determine if a point is in shot. And then you have to recursively compute what? Compute contribution from neighboring objects to this point. So meaning that you have to generate a ray, or reflect, a ray from this point to neighboring objects, get a contribution from this point, and this point recursively then would, see if you would get contribution from another point, etc., etc. This is a recursive process. This is the third step. And then if the object is transparent, you have to go through the object to get contribution from light sources and the neighboring objects from object behind this transparent object here. This is your fourth step. Okay. That is why your ray tracing process cannot be, you cannot use the pipeline to do the computation for ray tracing process, because recursive means that for each of these steps, you have to go through that pipeline again. And this recursive process could go to 10, 20 objects. Okay, that means you have to go through that pipeline 10, 20, maybe even 30 times. Okay, that's why you cannot use that pipeline. Okay, you have to use the cores separately. Okay, so step one, step 2, step 3, step 4, etc. Right? And your C program basically is what? Is to provide administrative support, logistic support for what? For your computer shader program, for your vertex shader program, for your fragment shader program, such as define texture and screen windows width, height, administrative steps, or provide data for the computer shader program, or provide protocol variables, provide the buffers for the vertex shader program, for the fragment shader program. Okay, so your C program basically is just to provide administrative or logistic steps. Okay, but you need to know how to do those steps, even though those steps, in my view, are quite standard. Okay? So you have to provide your C++. Your C++ tool has to provide, let me repeat, administrative and logistic support. Like, define the size of the grid that you can use. Grid of what? Cores that you can use for your task. Right? So ignore this part. Okay? These are just steps that we need to support the execution of your computer shader program, your vertex shader program, your fragment shader program. Okay? So basically, these are, and your result will be rendered as two triangles. A square will be split into two triangles. remember that the GPU graphics pipeline is triangle-based. Okay? Triangle-based. So if you have a two-dimensional array, that array has to be split into two triangles. All this has to be done by your C++, by your vertex shader program, but the support has to be provided by your C++ program. Okay? So this is phase one, to call the computer shader program to generate a texture image, a 2D texture image. And then once the texture image is created, then you have to use your vertex shader program, your vertex shader program to have what? To have that texture image rendered on the screen. This time you use the pipeline. Okay. This time you use the pipeline. So, up to this point, I didn't say anything about computer shader program. Remember, that's your job. That's the program's job to write the shader the computer shader program, the vertex shader program, and the fragment shader program in GLSL language. So you don't have to worry about this part. You don't have to worry about this part. So this is the entire process here. First, your phase one. You use enough cores of your GPU to finish the work of generating a texture image for each ray, for each pixel of your screen. And then once this is done, then you use your vertex shader code, your fragment shader code to have this texture image rendered on screen through this GPU pipeline here. Okay. This is your phase two. Phase one here, of course, is the majority. You have to use as many cores you can get to finish your one. In this case, your ray tracing process. Okay? So, here is the facts. Here's the set of facts. Most of the steps that I didn't show you are standard steps, such as the init function, the display function, and the two defined protocol variables, communication buffers. Okay? These are standard steps. Okay? And you have to write the computer shader programs, vertex shader programs, fragment shader programs, okay, to do the task and to have the result rendered on the screen. These shader programs have to be written in GLSL language. So in addition to know how to write a C++ program, you always have to know how to write a GLSL language. Okay? So here is the question, first question for us, for you and for me. Is it possible to build a PC net with 100 or 200 laptops so that what? So that build a PC net, okay? So that we can have as many as 250,000 or even 500,000 cores to perform parallel tasks with a relatively cheap construction cost, less than 200K. Okay? And yet, since we have this many cores, we can have the performance of $1 million supercomputer. Your cost is this, but you can do work as big as those things handled by a $250,000 supercomputer. So why do I think that this is possible? Okay? What we need here is to have a control unit, such as a server, right? Such as server, right? That can install copies of a computer shader program on all the GPUs in the net. In addition to its own GPU, that CPU can also install shader programs on other GPUs of those machines in the net, okay? And assign task IDs to those copies of the GPU, okay? And create buffers for the CPU to communicate with those GPU, I'm sorry, this is type of GPU copies, right? So instead of having a GPU that can do work on its own CPU on its own GPU, we hope that this CPU here can also install the same computer shader programs, vertex shader programs, fragment shader programs on the other GPUs as well. If this is possible, then of course this would be possible to build a PCnet with this many laptops or desktops so that you can do things that usually can only be handled by what? Multi-million dollars for a computer. Okay. So this is the first question. Now here's the more challenging question, the second question. Currently, most people's laptops or desktops GPU computing power is not used at all. You have a laptop with a very powerful GPU, but that GPU is not actually used at all, most of the time. Most of the time. Only the CPU's computing power is used. So a lot of computing resources is wasted on those laptops and desktops. The main reason, of course, is because most people do not know how to write GLSL shader code to drive the GPU on their machines. Okay? So we don't know how to do this part. Most of the people. Okay? How to do this part. Now, what has already been done here is, for instance, Python programming can be compiled directly from GPU and CPU, right? And the jobs of Google can use the cores of a GPU to do parallel computing directly, right? Only if you know how to use jobs of Google, right? So here is a very ambitious question. Is it possible to bind the CPU and GPU together so that the CPU can automatically generate GLSL shader code to drive the GPU to do parallel computing on every task? What this means is that when you write a program on your laptop, a C++ program on your laptop or desktop, okay, that program will automatically generate required compute shader program, vertex shader program, fragment shader program, so that the task that you are going to execute, okay, will then be also executed by what? By GPU, because you have what? You have a computer shader program, you have a vertex shader program, you have a fragment shader program. Those programs can be compiled, linked, and then activated to drive the GPU to do that task. Is this possible? Is this possible? So meaning that now a program, once a C++ program is generated, then the GPU will automatically create what? A computer shader program, a vertex shader program, a fragment shader program, and have those programs installed will, of course, compile, read, and execute, and install on GPU, so that GPU can execute those instructions, okay, in addition to CPU, or simply execute those instructions on GPU, because GPU has more computing power than CPU, and then have the result either sent to back to CPU or sent to display log. Is this possible? Is this possible? Is this possible? I think the answer is yes. I think the answer is yes. If what? If we can develop a GLSL.cpp, a library, and develop a GLSL.h editor. So, if this is possible, if we can generate a library in a header file powerful enough so that each time when you write a C++ program, then that C++ program will automatically be translated into what? Into some computer shader program, some vertex shader program, some fragment shader program, and then be sent to GPU to do the execution of the original task specified by your C++ program. So this way, your GPU will automatically do computation each time a task is assigned to CPU, and you will get a better performance because remember, GPU has many more cores than the CPU, even though each core is not as powerful as the core of the CPU. So, the question then is it possible to generate such a library? It's possible to generate such a header file for us to automatically convert the C++ program to required computer shader code, vertex shader code, and fragment shader code. If this is possible, then conceptually, this is eventually what we are going to see. Integration of the CPU and GPU into a functional unit. They are still separate hardware pieces, but they can now function together as a unit, because your CPU now has control of the GPU. Your CPU now has control of the GPU. Eventually, if this is possible, then eventually you can actually build a CPU and GPU into a single physical device instead of two separate devices. Okay? But first of all, you have to prove that this is possible. You have to prove this is possible. And remember I said, I think this is possible. If we can develop a GLSL CPP library and GLSL header file for us to automatically do the translation. Okay? Once this and this are included in your C++ program. Okay? So this is the second question for me and also for you. So this is the idea of using computer shaders to parallelize certain tasks on a laptop or desktop that supports OpenGL 4.3 or up. Any questions? Yes?
I don't understand what's the component of the PC that would make it perform better than the supercomputer. The supercomputer would have still so many GPUs, and therefore so many.
Well, I'm not 100% sure of that part. Okay? much for a supercomputer because supercomputer is much bigger computing power. So this is just my estimate. If you can put 100 or 200 laptops together by combining all those cores from those CPU, from those laptops or desktops together. This question actually has to be answered by people, in networking or those areas, if this is possible, because you need a lot of communication between those units instead of using a simple supercomputer.
So is the cost of a very single powerful GPU that is like a supercomputing GPU more than 200,000 smaller GPUs? Is it just more expensive?
Well, my estimate for that part is that usually you only pay less than $2,500 for a very powerful laptop or desktop. So if you link all those laptops or desktops together, 200 times 2,500, you have to pay approximately $250 million more instead of $400 million, or even tens of millions. Yes?
A question about the computer, the compute shader. Do you have to have a different one for every scene that you wish to render, or will one work for all scenes?
Yes. That's why you need. That's why I think you need to develop or to create or to build a very powerful GLSL CPP library.
I didn't understand your answer. I asked an or question and you answered yes. Which of the two was the yes?
All right. So the library here should have a function to support, say, ray tracing. A function to support, say, matrix multiplications. Libraries to support, say, image filtering. Libraries to support particle systems, etc. Each of these is a big job. So this thing, other people might have thought about this, but I don't know if they think this is possible for them to do. But for a department or for a university, at least we can start the first step or second step.
But before we even get to this idea of using multiple CPUs, if I'm just wanting to build, going back many slides, a compute shader, does that compute shader depend upon the scene that I wish to render, or is it generic for any scene?
Depends on your task.
I just use ray tracing to render a
The
scene.
ray tracing is only the core, okay? But to support this thing, you need many administrative steps, logistic steps, okay? We can standardize those steps. And for those, core documentation, when you have a C++ program for that part, then you simply copy that into your shader program, your compute shader program. Translate into GLSL language instead of C++ language.
Okay.
Does this make sense?
Yeah.
Right. If we can start this work here, okay, maybe we can do something together under the leadership of our senior people. I think this could be a good project for us. Any questions? Any questions?
I think I will take over and say thank you very much for the first presentation this semester. We are looking forward to all the ones that will follow.
Well, I promise you that we will have a set of, presentations, but I cannot guarantee we as exciting as this one.
We know that. Thank you very much.
All right. Thank you. So, please enjoy the piece. But before that, you have to sign in.